In this video, we will demonstrate the steps to review an SRH 2D model and how to use SMS to visualize results. FHWA has created a model review spreadsheet to help provide steps for users reviewing SRH 2D models in SMS. We have opened a copy of this spreadsheet. This can be found in the input folder for this lesson. This Model Review tab has a list of over 100 items you may wish to check during your review of a model. For example, terrain data, mesh, boundary conditions, structures, and so on. There are other tabs for specific review items with space to make notes, provide detailed comments, and add images. These other tabs also show examples of common issues. For example, for topography, there is a section for notes and graphics to the right showing common issues. Next, let's do a quick review of the model in SMS. First, we'll look at the mesh. We'll turn on elements and turn off the contours and the image to better see the mesh. Next, let's zoom in and pan to review the size and shape of the elements throughout the model. Next, we'll turn on the mesh quality option as well. Remember, mesh quality is just a guideline, and you don't need to remove all of these warnings. For this mesh, we see mostly element area change at the mesh transitions, which should be okay. We can also create an ARR plot at this point. Note that all points are above the red line, indicating a good quality mesh. Next, let's review the elevations. First, let's turn the elements off and turn the contours back on. Now we'll look at the elevation contours in general. Turning the lighting on can help visualize the elevations. It is also helpful to use the Rotate tool to review the mesh elevations. Note that the mesh elevations capture the channel and other critical features. It is a good idea to review the boundary conditions. We'll switch to the map data and turn on the BC coverage. We'll double-check on both the upstream and downstream BCs to verify they are accurate and reasonable. Next, we'll look at the simulation plots created when the model was run. These can be accessed by right-clicking the simulation and selecting Tools, View Simulation Plots. These are the same plots that appear in the simulation run queue while the model is running. Let's look through the plots. First, there is NetQ plot. Recall that the NetQ should converge to 0 when the model has reached steady state. The mass balance plot should approach 0. The wet elements plot should level out, indicating the storage has filled and the model has reached steady state. The monitor point and monitor line plots can be used to review model results at specific locations. These plots can also indicate steady state convergence if the values flatten out and stabilize at a constant value. They can indicate instability if the plots oscillate or do not converge. Next, let's review the data sets. First, we'll look at the velocities. Let's turn on the vectors and set the vector placement to on a grid at 15 pixels. We'll zoom in to view the velocities, especially at the bridge. Now let's review the water surface elevations. We should be sure the data values seem reasonable. Now let's look at the contour options. Note the different options for range, contour intervals, legend, and labels. If we click on the Color Ramp button, we can set color palette options. Hue Ramp is the default, but if we select User Defined, the FHWA palettes are available. Another useful tool is the Dataset Toolbox, which is accessed from the Data menu. The most useful tool is the Data Calculator. With this tool, you can perform arithmetic calculations to create new datasets. As an example, we can create a new dataset for unit flow by selecting the velocity dataset and multiplying by the depth dataset. We'll name this new dataset Unit Q. Note the new dataset in the mesh data. The Dataset Toolbox also has tools for comparing datasets, filtering, and so on. We can use an observational coverage to create plots of our solution datasets along arcs. To do so, first we create an observation coverage. Next, we create arcs where we want to extract solution data. Now let's create an arc along the center line of the channel. Now we can create an observation profile plot using the Plot Wizard. We select Display, Plot Wizard, or simply click on the Plot Wizard macro. In this window, we select Observation Profiles as the plot type. Next, we select the arcs we want to plot. In this case, there is just one arc. We'll then click on Specify Datasets and select which datasets to plot. Let's choose the Z and the water elevation datasets. This creates a plot along the arc for the two datasets selected. We can do this along any arc we create. We can also use the observation coverage to extract solution data at specific points. To do this, we can create points in this coverage. Then we can double-click on any point to bring up the observation coverage dialog. In this top section, we need to set up measurements to specify from which dataset the values will be extracted. For example, we could create a measurement called WSE by selecting 2D mesh and the water elevation dataset. The extracted solution at this point will show here under Computed Value. This feature was created to compare computed values to observed values for calibration, but it can be used to extract data at any location. Similarly, we can extract flow values across an arc in the coverage. Let's create an arc across our flow at the bridge. Now we can double-click on this arc to launch the same dialog. For arcs, we create a measurement called flow or flux. We select 2D mesh, then we select depth for the scalar dataset, and leave velocity as vector dataset. The flow across this arc then shows up under Computed Values. Next, let's create a flow trace animation. First, we zoom into the area of the model we want to include. Then we select Data, Film Loop. In this dialog, we can specify the name and location for the AVI file. Then we select the Flow Trace option and click Next. In this dialog, we can specify time options. Let's just accept the defaults. The next dialog allows us to change the options for the light particles that are placed in the velocity field. We can play with these, but we usually just select the defaults. Finally, we have a dialog for specifying video options. Again, we just leave the defaults and select Finish. SMS will create the animation in the location we specified and play it in the video player included with SMS. This animation helps us visualize the vector field for the solution. Lastly, let's show how to display an image on our mesh using the texture mapping feature in SMS. We select Display Options and select the General options. Under Texture Mapping, we select 2D Mesh. Now when we rotate the view, we can see the image draped on the surface. Shading can be edited under the lighting options to give the image a more realistic look. This concludes our demonstration for reviewing and visualizing SRH 2D models in SMS. The exercise that follows will give you additional information and practice.